and 40 minutes for the second. Good morning, ladies and gentlemen. On the second day of our workshop on the mathematical modeling simulation optimization for societal changes in scientific computing, I think the first day was fruitful, at least as was reported by colleagues. And we start the second day with a session for open porous media flows. We'll have two speakers with 3 lectures. For the first 2 lectures, let me introduce you Atgeirr Rasmussen from SINTEF, senior researcher of SINTEF. He will be speaking first on the OPM, the mathematical framework, and then the OPM Flow for the end-user application. This is the first part of this morning session. Atgeirr.
Thank you very much, Sultan. So, as Sultan said, I'll speak about OPM first and then OPM Flow in particular second. So about OPM, I'm going to try to answer a few very simple questions: who, why, what, and how. And I'll try not to go into much detail on this. However, on OPM Flow, I will go into quite a bit of detail, since that is the main pilot for us in this project. So, Open Porous Media, the Open Porous Media initiative was started in 2009. And since then, various components and parts have been developed by various parties here. Oh, I see it's an important thing missing is we now also have TNO, the research institute from the Netherlands, should be one of the research institutes contributing. But Statoil has, and still is a big contributor. Total has contributed. SINTEF, where I'm from, IRIS, TNO, University of Stuttgart, NTNU, and also various consultants have contributed to this software. Have come from industry and also from the public. Public funding is from the Research Council of Norway and from the EU through this project. And I'll just say that open source allows easier collaboration between different types of entities and organizations, such as companies, universities, research institutes, and also between different countries. There's much less need for ironclad contracts guaranteeing everybody their rights in a way that everybody is happy with, which is always very difficult to find in non-open source projects. So why OPM? So one very simple way to put it was that we had done a lot of work on advanced grids and discretizations at SINTEF. At the University of Stuttgart, they had been doing advanced fluid models through first UG, MUFT UG, and DUMUX. And Statoil had a lot of industrial know-how and were willing to fund work to put these things together, to make things happen. Our vision used to be, and still is, to have a long-lasting, efficient, and well-maintained open-source software for flow and transport in porous media. So, and our ambition is to be a strong base for both industrial development and academic research. So, we're trying to go from this picture below, which is kind of an exaggeration of the way it was before, where industrial companies get their software from software providers like Schlumberger, others, and these companies again have research contracts with research institutes and other research communities, and it takes a long time for new things from research to make its way through the providers into the software and then into the industry. And the direct connection between the industry and the research community was, I think, not, I am exaggerating a little bit, but it was certainly not direct, in the sense that only very limited scope software and methods were actually directly taken from the research community and into industry companies. So with OPM, we want to have something more like this. And I think we are succeeding where there's a tight and direct connection between industry and researchers. Because we collaborate on a project, we collaborate on the software with people both in industry and in the research community, actually committing to the same repositories and collaborating very directly. So why take OPM into this MSO4SC project? So one point is that we need to take OPM to where the usage is going to be. The cloud, large ensembles, larger scales. This is happening, and we need to be there. Otherwise, we will get obsolete. And another point, which is very important to me, is to have improved visibility and dissemination. We want to get more users, to get more feedback, to get more contributors, and also, from SINTEF's point of view, to gain new clients for our research services. And for that, visibility of what we do is important. Finally, to improve the OPM software itself, as a goal in itself, to improve its deployability, usability, and scalability. So, what is OPM? First of all, it's a set of software packages written in C++. There's a reservoir simulator Flow and a visualization tool which is specialized for reservoir data called ResInsight. And I'll demonstrate these two later, so I won't go into much detail about those. There are upscaling tools for physical properties. I'll talk a little bit more about the upscaling tools. And pretty new, there's a so-called flow diagnostic tools. Flow diagnostic tools are not simulators. They are cheaper, easier, faster to run than simulators, require a lot less resources, compute simplified properties, but can still give you quite a bit of insight into a case or a field. And also there's a toolbox. You can say that OPM as a framework is a toolbox with components for a wide range of porous media flow. So, but also very important is that we have open data, which in most research communities would be considered very important to have, and there would be good data sets available. But in reservoir simulation, I would say that that's not the rule, that data sets are openly available. Most data sets are closely guarded secrets of the companies that produce them at great cost. It takes a lot of money to do seismic surveys, and there's a long process from sensors and seismic surveys to a model that you can use for simulation. And they are therefore considered very valuable and usually not shared with the public or even researchers. It can be very hard to get access, even for research purposes. But there is one full real field case made available by Statoil, the Nune case, and I'll tell you a little bit more about that. We also have some of the benchmark cases that do exist from Society of Petroleum Engineers Comparative Solutions project available, and quite a few testing data sets for OPM software. So, and all of these data sets are made available under an open license, so that anyone can use them, change them, and benchmark their own software against using them. So I was going to say a little bit more about upscaling, since that doesn't get its own talk. So upscaling is about finding effective coarse scale parameters. I don't know, do I have a pointer, Sultan, somewhere? Oh, I have this one, the built-in. So, so if this is a fine scale part of a model, and the resolution of this model is too high for you to simulate it in a reasonable amount of time. You want a resolution more like this. Of course, this is just an exaggerated figure. But then you need to compute upscaled properties for each of these coarse blocks. So this coarse block corresponds to these fine blocks. You take out this block, it looks like this. You compute an upscaled property, which is an effective property to use for simulation. Oh, thank you. It's, need to, It says it thinks it's a keyboard.
Just close it and just use a pointer.
Yeah, of course. And that's what's the laser part? This one? No.
The top button.
Yeah, there's. Thank you. Okay, so for some properties, this is very easy. For example, porosity. The upscaled or effective value of a porosity is simply the average porosity. So you get a single value. So this is an example of upscaling porosity. But for other values like permeability, it's not so simple. For example, even if the permeability is a scalar value in this fine grid, the upscale values, it's going to be a tensor valued permeability. So that's due to layering, for example, and the grids being heterogeneous. So these are typical grids. This is slightly exaggerated in the z direction here, model of a domain that we want to upscale properties for. So and this is a typical grid for an upscaling. And this is a zoomed in on a part of this grid here. You see there are parts that are layers that are eroded out, and the layers are going up and down and so on. So it's and this is a typical case, not a particularly bad one. There are bad ones, but this is not bad. So for such cases, simple averaging is insufficient, and you must do flow-based upscaling. So flow-based upscaling means that you solve a flow problem, and then from the solution to that flow problem, you recover the effective properties. So, okay, I'll say a little bit about the Norne dataset. And it's the only publicly available real oil field dataset. It's a Norwegian sea oil field, so it's outside the north of Norway, or the middle of Norway, mostly. A very nice thing is that it includes historical production rates and measurements, so you can actually try to do better in terms of simulating it than those who have come before you. You can simulate it, you can run the simulation case with Flow, you can run it with commercial software, but you're also free to try to do better than either of these tools, because the measurements are in there. Oops. It's not very large, 45,000 cells, but it has quite a few interesting features. I'll mention just a few. It has faults. You see, this is the part of the simulation grid. You can see that these cells here are connected, but then the layers split apart like this, so they are not connected. Or rather, some layers here are connected to different layers over here, geologically. So flow in this domain is constrained and controlled by the faults to a large extent. It's got a fairly high level of heterogeneity, and the properties are far from uniform. It's anisotropic. It has lots of ill-shaped cells, so if you're expecting cells to have nice shapes, this is this has some horrible cell shapes. Oh, sorry, I'm missing it. And it has some more or less horizontal wells, which has its own challenges related to how it connects parts of the reservoir that would otherwise not be that tightly connected, and also because it means it challenges you in how you model the wells. So finally, how? We do all our development in the open on GitHub using the pull request approach. So basically, this is yesterday's list of pull requests in one of the repositories. I see it's far too small for you to actually see it, but and then there's this is just an example of when you open such a pull request in GitHub and see what it looks like. This is pull request number 1186, faster ILU implementation. So which is made by a researcher at Iris in Bergen in Norway, and then people from Germany and Norway have commented on it, and yeah, so it's so we comment on each other's pull requests, review them, look at them, discuss them, and when we're satisfied with, we merge them into the whole. We do continuous integration using a Jenkins server. So this is this here is from the GitHub discussion. You can, or if you are a maintainer, you can write Jenkins build this please into the discussion field, and the Jenkins server will get the message and build it and test it. So this is a very nice feature to have for a pull request. That means that every pull request can easily be tested. And there are some more things we can do with this that I don't show. We do regular releases every 6 months. The 2017-04 release is the current one. For collaboration, we have almost weekly hangouts between mostly SINTEF, Iris, Statoil, and some others to make everyone work towards the same goal. And it's very important that we avoid duplicate work by discussing who does what, because not everybody working on OPM is sitting in a single office or single building or single city or single country, but we are distributed. So coordination is a challenge, and we have found that rapid video meetings are very important for this. It's well worth the time. So for communication externally with users and get in touch with other developers, we have a website, mailing list, and we use the GitHub issues feature to get feedback about bugs and things like that. So that was all about OPM. Thank you. I'll immediately switch to the next talk because, yeah, we're on a limited time budget. But first, are there any questions about this before I move on to OPM Flow? Yes, please. Or stop, please. Yes, please.
Regarding the grid, it's just a scientific question out of curiosity. For this kind of meshes, can you handle things like polygons or are they like
you think of this kind of meshes?
And yeah, what kind of shapes can you handle?
This particular type of grid is called a corner point grid. It's constructed from pillars, so each stack of cells is constrained by 4 pillars, and the pillars need not be parallel.
Okay. And
for each cell, you are given the set coordinates of the bottom 4 and the top 4 points, so they are pretty free-form in shape. Properly speaking, the top and bottom surfaces are bilinear surfaces, and the side surfaces are subsets of bilinear surfaces. But it's a rather nasty grid format, to be honest. Our computational kernel deals with arbitrary unstructured grid, and by arbitrary unstructured, I mean not in this unstructured in the sense of tetrahedra, but in the sense of arbitrary topology, arbitrary cell shapes.
Okay, because there is a lot of development on virtual element method, and I was wondering if you are looking into this.
We have done research on using the virtual element method on grids like this to compute mechanical, to study mechanical properties. So yes, the virtual element method works well on this, and it's also related to the mimetic method, which is the discretization we have used for the upscaling part. So these are closely related.
Yeah, my question is if the software is taking into account geochemical reactivity between rock and fluid by simulating. You might answer this question later, but...
if you're talking about OPM Flow, the answer is no.
No. And are you planning to take into consideration?
We had some plans 2 years ago. That project didn't happen. We still want to do it.
Okay.
So yes, we want to do it, but we need to have sufficiently interested industrial and/or public parties to fund it. So because it's a major undertaking.
Okay.
But yeah, we have made some experiments, and we think it's definitely doable to do ion chemistry with salts becoming part of the rock and dissolving,
yeah,
and
dissolving and precipitating.
Precipitating, yes. That's exactly what we were looking at in that context.
Okay.
Because it's important in many carbonate fields on the Norwegian shelf, and yeah, so it's considered a probably important thing to have for many kinds of studies.
Okay, thank you.
Okay. Then I'll go on. So I'll have to say, sorry, Esther, I started this, creating this talk before there was, you published this template. So this is made with, you know, a straight beamer with an old template of mine, but at least I managed to put in the logo. I hope that helps. So, so I'll give an overview and brief demonstration of OPM Flow, and also a little bit about ResInsight. So first I'm going to talk about reservoir simulation in general. Then I'm going to show you the mathematical formulation, and some of you might choose to turn on your screensavers at that point. I hope to carry the rest of you through. Then I'll discuss how we have implemented this using automatic differentiation, and then a brief what's next. I wouldn't call that an overview. It's more like some of the things we are thinking of doing. I don't even mention the chemical things there, for example, but it certainly has been thought of and is still thought of. So reservoir simulation is to simulate flow in a porous medium in subsurface reservoirs. And the reservoirs being subsurface means that you usually don't have a really good idea about its properties. You may have seismic surveys, you may have well logs and so on, but you cannot take it up, look at it, that's the way it is. That's just impossible. So, so you're starting from a quite limited set of information. And creating just the simulation grid, creating the simulation case is a major undertaking in itself, which I'm not going to say much more about, because this is about reservoir simulation, which is what happens after you have created the simulation case and you want to get the results. So important examples of use are in the energy industry for forecasting and optimizing production of oil, gas, and also geothermal energy. And groundwater flows and pollutants are also an important use case for reservoir simulation. And CO2 storage, CO2 sequestration has become important in the last, say, 10 years, to study, to look at how is it safe, is it effective. So, reservoir simulators solve systems of nonlinear partial differential equations that are coupled to well or facility models. So that's the basic mathematical approach. So why is this hard? First of all, the porous medium is strongly heterogeneous and anisotropic, which means that, as a consequence, cells are usually usually don't have nice shapes. They usually have large aspect ratios. Typical cell might be 50 by 50 by 2 meters, or well, plus minus a lot, but they typically have quite high anisotropic ratios, and also anisotropic and heterogeneous effective properties like permeability. Oh, I already said this, and I also already mentioned that the grids are usually fully unstructured due to the faults, especially. And phase here I'm seeing non-trivial phase behavior is non-trivial, yes, and it's also a part of this. Phases can appear and disappear. For example, the light hydrocarbons can dissolve into an oil phase, so then the gas phase disappears, and then the pressure drops for some reason, and then below the so-called bubble point, and then the gas will come out of the solution again as the solution becomes saturated with the gas, and you'll have a free gas phase again. So that's part of what makes it difficult. So, and well coupling can connect regions that are far away from each other. And also the models are usually highly nonlinear. So this is an example of another of this bad grid. This is a candidate for the worst looking. Although it's actually very nice because it's in a shoebox shape, so it's not that bad. But its interior consists of really undulating surfaces that make any reasonable discretization not like this grid. So you have to use unreasonable discretizations, actually. And this is just the same case you saw before, the Nune grid. I think it also shows the wells, but they are, or some wells at least, but they are very, they're not very visible, but you can see here's a well, here's a well, here's a well, here's a well, here's a well. And these are just points where the wells come up out of the reservoir. Down in the reservoir, they have usually a shape like this. So why does this require HPC or cloud computing? One thing is that model sizes are increasing. Saudi Aramco recently set a new record by with their so-called powers reservoir simulation software. They now call it, they used to call it gigapowers for a while, since they had simulated on 1 billion cells, and now they have simulated on 1 trillion cells, so they call it terapowers now. So on one hand, these are just bragging points, but on the other hand, it's really shows that some actors in this field are really pursuing the extreme scale in terms of simulation grids. We are at the other end, to put it like that. We're not really pursuing this, not at the moment, eventually, maybe. So model complexity is increasing. We are looking at more complex well and facility models and more complex fluid models. There are new mechanisms that are becoming important, such as injection of polymer, injection of CO2. These mechanisms, many of them, require a better resolved fronts. Fluid fronts are often self-sharpening in some cases. But for these cases, the fronts are no longer self-sharpening, so you need to have a finer resolution, either using higher order methods or using higher grid resolution to get them resolved. And we want to do large ensembles for history matching, optimization, and uncertainty quantification. So the market situation, I'll say a little bit about that. So there are commercial reservoir simulators, which are expensive, but they are in general quite good at what they do. So Eclipse has been the most popular reservoir simulator for many years. And you might say it's the industry standard. So the input and output formats that we support are basically compatible with Eclipse input and output formats, because it gives the lowest barrier for existing users of reservoir simulation software to use OPM. There are many more. Intersect is Schlumberger's latest reservoir simulator, they try to get people to replace Eclipse with Intersect. They're not succeeding 100% in that because Eclipse still is very popular. Computer Modeling Group is another actor in this field. They have some highly regarded simulators. There's a Russian company that has a product called T-Navigator. There are many more. Each of these have their own special features or things they are particularly good at to attract customers. Then there are lots of in-house simulators. That's gigapowers. Oh, I should say terapowers now. Sorry for this. I forgot about that. There's like more. Shell has its own. Many more oil companies have their own in-house simulators and do not use the commercial ones as their primary simulators. There are Stanford University has a general purpose reservoir simulator, GPRS. But in general, all of these in-house simulators are not available to outsiders. So some are available to researchers if you manage to become an insider in some way, join a consortium or something. But they are not open source. They are not sold commercially. They are usually simply not available to most people. So then there are open source simulators. There are essentially only two. There's OPM Flow, and there's the MATLAB Reservoir Simulation Toolbox, which is also created by the group I'm in at SINTEF. The difference, one difference is that MRST is written in MATLAB, so it's slower, but it's also slightly easier to use as a prototyping tool if you're familiar with MATLAB, whereas OPM Flow is written in C++, and it's designed to be, or intended to be fast, and you don't need MATLAB to run it. So OPM Flow at a glance. This slide is, I think, quite similar to one you saw yesterday. So I'll just sum it up. It's studied open source. We handle cases of full industrial complexity with competitive performance relative to the commercial and other solvers. And it's currently used for oil production studies, enhanced oil recovery, and CO2 sequestration studies. So, and it's implemented using automatic differentiation to have rapid development of fluid models. I'll say a little bit more, quite a bit more about that later, actually. So now the mathematical formulation. So first, what are the basic physical laws and behaviors that are important? Conservation of mass, of course, for each fluid pseudo-component, oil, gas, and water. And we conserve the mass of injected EOR fluids, for example, in extended models, for example, polymer, CO2, or surfactants. And the geochemical question here, conservation for ion species, I put it in parentheses because we don't support it, but we want to. And it would belong here. You would need to conserve the mass of each ion. And this is the basic mathematical formula. It's just conservation of porosity times an accumulation term plus the divergence of the velocity of that component equals some source term. So it's very simple when you write it down like that. So then there's Darcy's law. For a single phase flow, Darcy's law says that the velocity in a porous medium of a fluid is proportional to the gradient of the pressure, and we have to include the gravity, so it's the gradient of a potential. And then the K here is a permeability. So the permeability is a proportionality constant between the pressure gradient and the flow velocity, and then you divide by the viscosity of the fluid. So far, so good. This is not a law that has been derived originally from first principles, but actually from it's an experimental law. So Darcy made experiments and derived this law many years ago. For multi-phase flow, we have the concepts of relative permeability and capillary pressure. First of all, the flow rate is reduced due to the presence of other phases. So the flow rate of one phase is reduced because the other phases take up room in the pores. So there's less room for this for one phase to move. So this is reflected by Kr, the relative permeability, which is a function of fluid saturations. So this enters the equation here. Instead of the 1, you have the Kr. So the pressure differences between phases is also, I think, that's due to the capillary pressure. So you have to do pressure by phase and not one universal pressure for all phases. So the black oil model is what Flow implements. There are some assumptions here. We lump all the hydrocarbon species into two pseudo-components, oil and gas. So basically, all the light components are gas and all the heavy components are oil. And then we allow the oleic phase to contain both oil and gas components. So, and we give a ratio here for how much dissolved gas is there in the oleic phase. And we allow the gaseous phase to contain both oil and gas components as well, where there's a corresponding vaporized oil ratio, RV, which says how much oil has vaporized into this gaseous phase. And it's assumed to always be at thermodynamic equilibrium, so there are no transient effects in transitioning between the states here. And the assumption is also that the PVT relations are simple enough that you can just use a simple table lookup to get your densities, viscosities, etc. Usually a 2D table lookup, but still quite simple nonetheless. So some consequences are, first of all, people always confuse the oil phase and the oil component. So this is very easy to confuse, because usually we talk about the three phases, water, oil, gas, and the three components, water, oil, gas. But the components can be water. The oil and gas component can be in either the oil phase or the gas phase or in both. So properly gaseous phase, oleic phase, but in practice people forget that. So, and I will too, once this slide has become the previous slide, I will also forget it, and I'll talk about the gas phase and the oil phase, even though and not make a very clear distinction between them, only when I want to point out actually the difference. Another consequence is that you have three different types of states in any point. At any point, you can have a fully saturated state when all three phases are present. You can have an undersaturated oil state when there's no gaseous state. All the gas has been has dissolved into the oil phase and is still undersaturated, because when it gets saturated, then the excess gas has to go into its own phase. And there's an undersaturated gas possibility, which is just vice versa. All the oil has vaporized into the gas phase. So, and this is a subset of a more general so-called compositional model, where you can't, in general, look up in a table based on RS, RV, and pressure to find your densities and your viscosities, but you must solve an equation of state, such as Pang-Robinson. I put this in parentheses because that's something we don't currently support in Flow. So here's then the system of equations. So for each pseudo-component, alpha, we have this conservation equation. And I'm just writing out a few things here. Just note that the U here is the velocity of a component, the flux of a component. So V, on the other hand, is the flux of a phase. So this is like a mass flux of a component. This is like a volume flux of a phase. So converting for the water is just it's simple. It's just a proportionality. But the flux of oil it takes into account oil in the oil phase and oil in the gaseous phase. And the gas velocity, gas component velocity, takes into account gas in the gaseous phase and gas in the oleic phase. So that's part of the complexity here. And also these B factors, they are called inverse formation volume factors in oil speak, which they basically behave like densities. Think of them like densities. So, and they depend on pressure and on these dissolution factors and so on. So that's part of where the nonlinearity comes in. So also we want saturations to sum to 1, basically saying that our fluids fill the available pore volume. And there are capillary pressure relations. Basically, these things here are going to be functions of saturations. So that's another source of nonlinearity. And finally, Darcy's law by phase, as you saw on the previous slide. So what is this source term? I didn't say much about that. Those are well rates, usually. So you will couple your reservoir model to a well model. And the well models can be quite complicated or they can be quite simple, but usually they have their own unknowns, or at least one unknown, but often more. And, and they must be usually solved simultaneously with the reservoir equations. So this is another source of complexity. So these systems are discretized usually using first-order implicit Euler in time, first-order finite volumes in space, using the so-called two-point flux approximation. Now, this, you remember I said that for reasonable grids, you can use reasonable discretizations, but for unreasonable grids, you have to use unreasonable discretizations. This is an unreasonable discretization. It's consistent only for particular types of grid, but it's robust and works and give you an answer on arbitrary kinds of grids, which is why it's popular. So it's more important to get an answer than to get one you know is right, in some sense. It's of course that's putting a slightly too mathematical spin on it, but in some sense this is usually not strictly correct from a mathematical point of view, but still it works well enough. So, another thing, point about discretization is that we use phase-based upwinding of properties. This is rather common in hyperbolic equation solving. So, and why do we use these primitive methods of low order and sometimes even inconsistent? Well, historically, these things were solved with finite difference methods, and doing higher order finite difference methods is not something I would like to do. At least it's hard, and we need systems that linear solvers can deal with well, and they deal fairly well with these systems. It's already quite complicated to solve these nonlinear systems, but with higher order, it becomes even harder. And it's sufficient for practical purposes. The engineering golden rule, if it works, why change it? And discretization errors are often not significant compared to the inherent uncertainty given by you don't know the domain. You don't really know it. You have some idea about the properties, but you don't really know them to any precise degree. So, but quite a bit has been done. On consistent discretizations, there's something called the multi-point flux approximation and mimetic methods. And for the upscaling part, we use mimetic methods. For OPM Flow, we use a two-point flux approximation, a simpler one. Work has been done on higher order finite volume or discontinuous Galerkin methods and higher order time discretizations, but none of this is mainstream yet. But I'm saying, if and when it becomes mainstream, I'd like it to become mainstream through OPM Flow and not through someone else's software. And I think it's much more likely that it will happen in Flow than in some commercial software. So the discretized equations, they are they are superficially quite similar to the continuous one I just gave earlier. So basically, you have accumulation terms, this is first order Euler and discretization, and then you just have a discrete divergence term here and a discrete source term coming from the wells. And these discrete relations look very much like the continuous ones. But the fluxes for each connection ij between cells I and cell j are given by using something called Tij here, which is the transmissibility. So this is the two-point flux approximation. Basically says that the flux between two points is given by the difference in some potential times the transmissibility. So I'll skip this. I put it mostly in this to be as a reference if you're curious later. So then we solve the discrete equations. And for that we use Newton-Raphson. We need to solve large heterogeneous linear systems. These systems have unknowns of different types. You will have typically a pressure unknown and one or two saturation unknowns. So you have unknowns of different types, equations of different type, and you put all this in a single linear system. It's a challenging thing to solve. So it's challenging to precondition it. Some people claim that combination of CPR, which is a special method for these problems, with an algebraic multigrid method is the best, but jury is still out. Our default method is ILU 0 in a block way with this a block of equations and unknowns for each cell. You must modify the update to account for the phase changes. You must, when you change, a cell goes from containing no gas to containing gas, you have to be careful not to overstep too much and get into an oscillatory regime where it switches between gas, no gas, gas, no gas, and with no end in sight. And you will have convergence failures, so you need to handle that somehow, and the usual way is to then to cut the time step until it converges. So that happens fairly often. So I'll see, how much time do I have for this part? Not much at all. I'll say, what does automatic differentiation provide? The traditional process is that a human needs to implement the function, the residual function, and then the Jacobian, we can use do it on paper or use some other system to find the derivative, the Jacobian. And then we implement code for this, and we implement code for this from these equations. And for these rather complex nonlinear equations, writing out the Jacobian can take pages of a research article. So it's really nasty and very easy to make a mistake, either in the symbolic derivation or in the implementation, especially in the implementation. So with AD, you implement code for the residual, but then you get the derivative, the Jacobian, for free. It's automatically generated. So this makes it easier to create simulators because you only specify the nonlinear residual and you automatically get the Jacobians. And you can also automatically get the sparsity structure of the Jacobians, depending on the type of AD you're using. It's not the same as finite differencing. You don't need to define an epsilon or something. You get the same precision as a handmade Jacobian, but with much less work. So performance of this, actually computing Jacobian, will usually be a little bit slower than a good handmade Jacobian implementation. Our first experiments with this, we discovered that our handmade Jacobian implementation was bad, because the first time we made an experiment with it, the new code using AD was twice as fast at the assembly part. So if you're very sure that you have an excellent, optimized, handmade Jacobian implementation, then don't use AD, unless you want to change it. Then you would be happy to use AD anyway. So The basic idea is to write a numerical computation as what was the term? When you evaluate one function inside the other, there's composition. Thank you, of simple functions. So, so this is the final. You want y equal to fn of yn plus 1, n minus 1, and then all the way down to yn equals f1 of x. So, and then the derivative, you get that simply by the chain rule. And there are two main methods. Use operator overloading, this is what we do, and the other one is to have an automatic differentiation tool that does source transformation. Source transformation requires you to stay within a subset of the programming language you're in, so that the tool can understand what you're doing and make the code for the derivative automatically. Operator overloading is easier to use, but requires a host language that supports it, such as C++. So, and then there are two types of AD. There's a forward mode, where you carry on with your derivatives with respect to independent variables. So your objects would, instead of being just a value u, it would be u and the derivative u with respect to x. And the reverse mode, you carry derivatives with respect to the dependent variables, so it would be adjoints. And yeah, I'll skip through this example. You can look at it afterwards. And a reverse AD example. And finally, a few notes about the implementations in OPM. We have a legacy implementation doing this in a vectorized fashion, and a new effort which does it single scalar value at a time. It's a simpler code in itself, and we do this because it turned out this gave much better cache performance, so it was more efficient. So we switched to that one. Okay, we keep pursuing performance, and we're looking at improving preconditioners and linear solvers, new discretizations, nonlinear preconditioning, parallel scaling. We're trying to improve usability all the time. Work has been started on a reference manual. We are getting more output or logging options and better error messages. Slowly but surely, error messages are becoming possible to read by engineers and not just the coder who wrote it. And deployability through container usage. We support Docker right now. Through the MSO4SC portal and web integration, and this should have been deleted. So further ahead, these are some of the possibilities. New fluid models, make it scriptable, more flexible boundary conditions. That's in particular important for groundwater pollution type cases, not so important for petroleum. Higher order DG methods, consistent discretizations, fully compositional fluid model, new I/O system for parallel scalability. Our I/O is currently serial, which is not a big problem as long as you are on, let's say, a single workstation, or up to, I'd say, up to 12 or 16 nodes. This has so far not been the big bottleneck, but it will be eventually. And what about pre-processing tools for creating these models? Going one step upstream from where we are now. These are just ideas. So thanks for listening. I'll have a little bit of time for a demonstration, but actually I don't. Do I? I used up all the time. But okay. Yeah. Okay. So this is. I'm logged into the SESCA system, so I'll and it has installed the simulator Flow. So now I just started a job running a rather simple test case. And Victor, you remind me, what command do I use to see if it's running, or? SQ, like that? What is QU, like that? Oh yeah, the this way. Yeah. Oh yeah, it's this means it's still running, right? Yeah. And now it was done. Okay. So I'll.
Excuse me, Andy. Can you make the font bigger, please?
Oh, maybe I'll try. That's not bigger. That's smaller. Oh yeah. Okay. Well, I'll switch to this one anyway. Done with that demo. Too late to make it.
Okay.
So, and then I'll just show you the results of this run in the ResinSight software. So this case is it's a very simple small case. So how do I So this case is a reservoir with you can see there's a water layer at the bottom, and then there's a transition to oil, and then an oil zone. And at this point, I lost my. Oh yeah, there it is. And you can see that as time goes on, well, something should happen here. Yeah, you see that the oil gets depleted by the production wells, which are all these wells here, and there's a single injection well there. But what I really wanted to show you was the gas phase. So at the start, there's no free gas. But as we start producing, the pressure drops below the bubble point, and free gas comes out of the solution. So there comes a free gas phase here. So just with that, I think I have to stop, and thank you very much.
Thank you, Abdelhakim.
So, any questions? No, feel free to talk to me in the break afterwards, or any of the breaks. Thank you.
Thank you. We need 1 minute break for changing the laptops. Okay, let's close the communication triangle that was shown us by Atgeirr, the triangle of researcher, software, and industry. Let's close it with an industry lecture by Rustad from Statoil, who is a senior researcher there, and we especially like this talk because it will be talking mathematics in the oil industry, and knowing that Alf is a fan of mathematics. So,
Thank you. Thanks for the introduction and the opportunity to come here and speak. So I was encouraged to give a kind of an overview about the mathematics we use in oil industry. And that's quite broad, actually. Myself, I am a mathematician, but I left academia for the industry almost 15 years ago. And that, I have to say, it's been a fantastic journey. I've had lots of fun. I can hardly imagine any applied mathematics that is not of interest to the oil industry. So for a mathematician, it's been really fantastic. So with a 20-minute talk, of course, that's going to be, I'm going to try to the best of my capabilities to give you an overview, but I'm probably going to fail utterly. But still, of course, many of the slides are going to be quite superficial. So I hope that you will ask me some really tricky questions afterwards. I really appreciate being put into a corner with difficult questions. Of course, OPM, now Atgeirr has given you a very good overview of that. OPM is something I really feel passionate about because the oil industry has not been very open traditionally, and OPM is an attempt to try to do something about that. We have a lot of challenges computationally. And these challenges, we see that within the oil companies, we don't really have the resources to tackle them fully. By going open source, we might be able to actually solve many more of these while there still is some interest for oil in the world. Atgeirr gave you an overview. I can also mention that we have a couple of other efforts also in OPM that is not as yet very visible. You will find also a framework for fracture modeling there now. You will also find a framework for pore scale modeling. And lastly, we also have some software coming for studying core flooding experiments. So, scientific visualization. I noticed that ParaView was mentioned yesterday on a number of occasions as kind of a main tool for this MSO4SC project. And of course, then one natural question would be why don't we use ParaView? Why did we start all over again and implement ResInsight? So I think that's a very fair question. There is at least two answers to that. One is that ParaView it appears to be the jack of all trades, but the master of none. It tries to be kind of too much to too many people, whereas what we needed was something that would be compelling to reservoir engineers to work with. And ParaView was, I mean, if you just look at the user interface here, you see it's very clean. If you look at ParaView, you will see that half of the top is covered by buttons. That's going to confuse users because it tries to kind of solve everything. Still, ParaView was not capable of solving what we needed. It didn't support the file formats we had to support, and it didn't really have the functionality we needed. Also, it resembled an open core project. Seemed like it was kind of tailored to make some proprietary adaptation to whatever you needed to do, and that was not what we wanted to do. We wanted to have a fully open source project tailored to exactly what we wanted it to solve, and also then to make it a success among users, which it has become. It's really been an extreme success. Reservoir engineers now increasingly prefer it over the expensive proprietary alternatives, regardless of price. And these kind of softwares, they are really expensive. And that, I think, is one thing that is very nice with the oil industry. It has put a price on mathematicians. Very few people in this world is willing to value mathematics. But in the oil industry, mathematics is really valuable. And it really creates business cases. That, I think, is really fantastic. So ResInsight, it was an answer to a very specific problem. We were able to simulate on models with Eclipse, the old Eclipse simulator, with models with more than 5 million cells, but the workstations we had at the time. And if you ever wonder who buys these expensive NVIDIA Quadro cards that costs a fortune, look no further. That's the standard equipment in the workstation in the oil industry. But even with a top-end hardware, so these workstations easily cost you $10,000 a piece. Even then, we had, with the proprietary viewers, we really could not visualize the results. It was too slow. If you tried to turn the model around, you could go and have a cup of coffee while the computer was thinking about it. So that was the problem we wanted to solve. So I find it kind of amusing that some oil companies are using teracell models. I have no idea how they are able to look at the results afterwards, but they may have some fancy visualization also. ResInsight, by the time we had it finished, the first version of it, and that was a year or so later, we were easily able to visualize 20 million cell models on these same workstations. So because of its design for performance, it's also now become a very important tool for looking at multiple realizations. If you want to do real uncertainty models, you need many realizations, and trying to co-visualize them is really a hard challenge for visualization. So now I'm talking way too much about visualization. I need to move on. Geomodeling techniques. I mean, if you ever, I thought, when I went to school, I had some geography with some geology, and I found geology very boring. But when I came to the oil industry, I found out that geology is really fascinating. It's a fascinating field where there's a lot of action, actually. I thought rocks were kind of dead things, but they're not. They were created at some point in time by a process. And these processes, they give rise to very advanced mathematical and statistical methods. So if you want some turbulent flows, sure, turbulent flows, if you want to model a depositional process for a rock, you have a turbulent flow. And it can get basically as complex as you want it. If you want some advanced statistical models, where you want to condition to all kinds of data, that's your geomodeling framework. And this is a place where we don't really have succeeded with open source software yet. We're still confined to very expensive software packages, and this is a very important part of the pre-processing. So that's also mentioned as part of the MSO4SC project, that the pre-processing tools. But I think for the foreseeable future, for reservoir simulation, it's just not feasible for this project to be able to provide a full suite of pre-processing tools. I would love to attack that problem, but I'm not sure when we will be able to get to it. Atgeirr mentioned upscaling, the more general problem, homogenization, which is a huge field within differential equations. And it really gives rise to some very interesting mathematical problems. Perhaps some of the most fascinating ones is when you go from the microscopic scale to the macroscopic scale. That is, if the real flow physics, it happens within pores. It's a porous rock. In the single pores, if you want to govern flow there, you have basically Navier-Stokes equation. But when you go to the macroscopic scale, as you saw, we have Darcy's law. So through the upscaling, you basically, your physics change, your laws of physics change. One of the parts there I really find fascinating is something called nuclear magnetic resonance. Most people know it just as MR, because in hospitals they don't really like to have the nuclear part explicit. People don't like to know that they're being radiated. But we use that as a measurement tool. So there is also some connections. There are several connections to medicine. And there, if you go to the pore scale, if you want to model the process of NMR, you basically have a Brownian motion. But if you go to the macroscopic scale, you have a Fredholm equation of the second kind, which is as bad as the integral equations gets, really. So a very tough inverse problem. Of course, system of PDs, Atgeirr really gave you the full ground course of the fluid flow. This is just a 2D section from a field. So rather than talking more about the system, coupled system of PDs, which is of course, it has given rise to highly specialized methods, like Atgeirr showed you some of. So it has grown into a whole field in its own right, really. But also based on the simulations, we want to cover uncertainty. And that has given rise to advanced conditioning and optimization methods. So these days we're trying to handle an ensemble of simulations. There basically you've seen two competing methods to condition this to the available data, because they're really a zillion unknowns. And if you go to the field of statistics, there's basically two methods that can help you if you have a large number of unknowns and a large number of data. That's Markov chain Monte Carlo, and it's ensemble Kalman filters. And both of them have been highly studied in the oil industry and been competing for usage as a history matching tool for ensembles of simulation models. And that's where you can see also these methods really put through the test, and you can see where they fall down. And right now it seems like the ensemble Kalman filters are really fallen down. They have been replaced by something called ensemble smoothers. Basically, when you start to work on real data, you see that the real data correlates too heavily. And these updates you do, periodic updates you do of ensemble in an ensemble Kalman filter, you assume too much information on the data. It turns out that this data you have over time, it's actually correlated over time. And to handle that, you have to go to the end of the simulation. You can't really do the updates all the way, unless somebody comes up with something more clever than what exists today. So the answer has been a method called ensemble smoother. Both of these are now actually already implemented in a commercial software package. Of course, I would love for it to be open source, but it's not. Sorry, it's extremely expensive software package called Tempest Enable from one of the software vendors. So this could be one of the areas where OPM or somebody else could step up and provide an open alternative. We also now see a huge focus on optimization. So what that's going to amount to, I'm not sure. But this is optimization, of course, is if you have the uncertainty modeling, it's natural to go the next step and look at if you have all these realizations that represents the uncertainty of your reservoir model, it's natural to also use them for optimization studies. And this gives also rise to basically the toughest optimization problems you can imagine. We do advanced laboratory measurements. I did mention NMR. We could call it NMR in the hospital, it's called MR. We also do the CT scanner. So that's the picture on the left there. It's from a core plug, which is the diameter of that is about 2 inches. So you see a flooding there, you see the water coming into the core plug. You see it prefers to go to the bottom of the plug. I don't think that's gravity really, it's probably just the fact that the flow property is worse on the top of the plug. On the right hand side you can see a picture of another plug, a cross section. It's done with an electron microscope, which allows us to really zoom in down to nanometer scale. We also push the technology for industrial CTs, because the medical CTs, they can give you the kind of resolution you see on the left there, but we want to see really each pore. We want to go down to nanometers, and then we need a kind of X-ray source that you would never use on a human being. So we're pushing the limits there too on what computer tomography can deliver, and that also gives rise to interesting mathematical problems. And my impression is that the oil industry today, they really don't have the resources to work on that. We are kind of relegated to whatever is finished products on the market. So we could use some more collaboration with academic communities, I think. Of course, mathematics of sound, that's also a discipline in its own right. The reservoir simulation, that's a discipline in its own right, typically called reservoir engineering. Mathematics of sound, that's what usually is called geophysics. People take their PhDs in that field. It's a very rich field with many problems, and also give rise to a lot of interesting mathematics. The first thing you do from a seismic survey is typically the migration, and that's where we see the HPC really coming into play today. It's a big consumer of high performance computing today, and the migration is basically when you do the seismic, you detonate an explosion, and then you have microphones typically dragged after a boat that records the echo from the explosion as it hits the underground. But of course that's just going to be a time series of sound. The process of migration is to place that sound signal somewhere in the underground. You need to know where that echo comes from in the underground, and that's the process of migration. And that, I mean, on that problem you throw as much computing power as you have, and that's where also the GPU has had some success in the oil industry. We have put up full clusters to do the migration. But the migration is not the only place where interesting stuff happens. Once you have the migration done, and once you have put the field into production, you also want inversion. That is from the sound signal, you want to say something about the properties of the reservoir. The typical property that the sound cares about is elastic properties. So that's your typical inversion parameter. If you do a 3D inversion, you invert from the sound signal and to the elastic properties of the rock with fluids in it. And there you need your wavelet analysis. We've had huge success by transforming the full problem from the time domain and into frequency domain. So that means we Fourier transformed the whole thing. And then you need as fast Fourier transforms as you can get. The sound signal itself is typically modeled as a wavelet. So there you go, all those typical wavelets you've seen, we do use them, and we also try to estimate wavelets that really match your sound signal. Probably spending too much time here, but as long as Sultan is not interrupting me, I'll take whatever I get. So we have, of course, well measurements. And that's really where I feel I've kind of failed. It's an area where I've tried to really do something, but I feel that at least I haven't been able to make much of a difference there so far. It's really fascinating. All kinds of measurements are done in the wells. They're called logging tools. We should probably feel kind of bad. We do all kinds of bad things. We electrocute the reservoir, we radiate it, we do all kinds of bad things to it, just to get some knowledge. Because we don't really know what's down there. Nobody has been down there to look. We can of course drill out the core, so that will give you the diameter of the well, the rocks from the diameter of the well, and you can have a look at those. But to extrapolate from the well and into the reservoir, you really don't know. You can of course use whatever geological competence you have to try to understand how the geology spreads out. But what you really want to also know, of course, is how much oil is there, how much gas is there, how much water is there. And then basically the only, oil and gas, they are made up of hydrocarbons, molecules. Basically the only hydrocarbon indicator we have, more or less direct indicator, that's electric conductivity. Because hydrocarbons don't conduct. And if you don't have hydrocarbons, you typically have saline water. And saline water is highly conductive. So that's why electricity is very interesting to us. So we have a whole range of tools just to measure the electrical conductivity of the reservoir. Two basic classes, they are called lateral logs and induction logs. The lateral logs, they do the easy thing. Basically, they have put in an electric current and just measures how much electric current goes from one point in the well to another one. Of course, that has been advanced to multiple points by now, but perhaps more interestingly, you have the induction logs, which induces an electrical field. And then basically you have to solve Maxwell's equations. And ideally, you would want to solve Maxwell's equations on a 3D representation of the underground. Because as Atgeirr showed you, it's really a three-dimensional object, this geology. And when he says heterogeneous, it means the properties really vary drastically from one cell to the next. And just solving, just for a very limited meter times meter model with a heterogeneous rock to solve Maxwell's equations is a very hard problem. And right now, we hardly even get to see the specifications of the logging tools, because that's typically trade secrets for the vendors. So it's more a fundamental problem. I did mention NMR, which is the Fredholm equations you see here. We've been on the NMR logs, we've been more fortunate. We have more knowledge about them, so we can do more of the modeling, and we have done so too. But unfortunately, they are not part of the standard logging suite. We also have sonic logs, which measure sound. We have neutron logs that measures basically radioactive measurements. We have gamma ray logs, which has a passive reading of the gamma radiation from the underground, and a number of other logs. For the future, I probably have to first say a disclaimer. The future is not set. I don't think anybody can give accurate prediction about the future, but of course that doesn't need to prevent us from trying. So at least, if it's not a prediction, at least a hope. I hope the future is open source. I strongly believe it is. And that's one of the reasons why I really like this project. And I also hope that open source can be an enabler to see a much faster technology development than what we have seen the last 30 years. That was all I was planning to say. I have no idea how much time I've spent.
Thank you very much, Alf. Have you got questions now?
Very nice talk, thank you. I wonder the one thing with the uncertainty quantification of the PDEs. So how many samples did you have there? So you were talking there.
Here?
Yes, this one.
Like on an ensemble?
Yeah.
Oh, yeah, that's a good question. I would say that depends on the engineer, basically. You can, I mean, there's nothing preventing you from having 1,000, 10,000. If you want to do history matching, I think 100 should probably suffice. If you start to use more, then it quickly gets unwieldy. You would, of course, love to have all kinds of uncertainties in there at the same time. The problem is that the poor human being needs to handle this in the end. So it's, but when you go to optimization, it's a bit tougher. And there, I think it's not quite set yet. There, because if you want to optimize, you can quickly find that you're going into a local optima. If you really want to span the space and be sure that you're not missing out on a much higher global optima, there's no limit to how many realizations you could throw at it.
Thank you for the very nice talk. If I go back at the beginning of your talk and actually also the conclusion regarding open source at what Atgeirr said. So Statoil or you, I mean, is it Statoil position regarding open source, or is it your position as a researcher? And what is the vision of the other either customers or competitors with this respect?
Yeah, that's a very good question. I'm not sure I have the full answer to that, but what I can say is that within Statoil it has become a clear strategy. So yes, Statoil wants open source. That doesn't mean that the companies, I mean, the company, there are many entities in a big company, and that doesn't mean that the company is ready to share whatever is being done. I think it's a learning by doing experience. But there is a strong willingness, and there is a clear strategy internally also that we want to explore open source and see if that can help us accelerate technology development, for sure. When it comes to other oil companies, I think you'll find a more mixed bag. Of course, it's not my place to talk down competitors, but I found that open source can be a tough sell in some occasions, yes. So, but not internally. Internally, it's been a fantastic journey so far. So all across the company, people are very enthusiastic and positive about it. Yeah.
Regarding ParaView, so the interface is too complicated, and in terms of file format and functionality, this is not up to your expectation. So this is what this is my interpretation.
It's correct.
But the thing is that this can be completely customized, because the core is actually the visualization toolkit. So you can completely brand your version of ParaView. This is, you build your own application and you decide what you have. If you want to have such clean interface,
for me, that's part of the problem, actually.
It's a lot of work to maintain the software.
I think it's a matter of philosophy. For me, it's part of the problem, actually. ParaView seems to be it gives the impression of being an open core development project. So it's permissively licensed. You are basically encouraged to make your own proprietary juice on top, just similar to Android. And that's not really what I want to be engaged in.
Okay. Well,
I have communicated this with Kitware, actually.
Okay.
Yes.
Good.
I have told them my concerns, and or at least one of them. Yeah.
That's good. I happen actually to know the head of the European
Yeah, I haven't met them. It was coincidentally that I met one of their developers and had a mail exchange where I communicated my concerns on this and why we did what we did.
Regarding the last part, more like on the, you are doing some kind of EEG of the, you know, like electroencephalogram, you know, what you do with the brain. You kind of do it with your electrical experiments in the ground or something like that, right? You want to characterize what's going on inside with respect to the electric conductivity.
Yeah. Yes.
This is like that.
But I don't. Was that? I didn't get that. Was it a question?
Sure, I understood what you said.
Yeah. That's one of the problems that gives rise to challenging mathematical problems.
He has a brain project.
You have a brain? Oh yeah. I don't know much about brains, I have to admit. So the connection to what is done on...
There are connections.
Yeah, I'm not surprised. But I wouldn't know really. I don't... I have very little knowledge about brain research.
But we don't do seismic experiments.
Seismic? Sound.
Any other questions? If not, I thank Al for the interesting lecture. Let me mention that Alf and Atgeirr will be here during the whole workshop, and you can approach them with questions. Just right after this session, there is a reserved time for a certain partner for consultation. Otherwise, it's still open, the schedule. I am showing the way to the consultation room for that consultation. And we would like to start with the next session exactly 11. Okay? Thank you.
Let it fill your soul. Let it fill your soul. Your soul. Let it fill your soul. Your soul. Your soul. Let it fill your soul. Your soul. Your soul. Your soul. Your soul. Let it fill your soul.
It seems that maybe there are still some people at the consulting room. But, well. Okay, so let's start the second session of this morning. We'll start with Lotfi, who's going to present an application from, I'm not going to say the institute because I won't be able to, but SZE.
I can help you if you want.
And on an electrical motor using C++, and then the Christophe Trophime and Guillaume Dollé will talk about the Hifimagnet application.
Thank you, Chairman. Ladies and gentlemen, the title of my application, my presentation, Application under FAIR++ Thermal Simulation in an Electrical Motor. The outline of my presentation, I start with the introduction. After that, I will talk about the geometry of the analyzed motor. And after that, I will present a few previous results that we do under Fluent and Abacus. And after that, I will talk about the motor losses, terminal analysis, heat source model, and the proposed or the planned method to solve this problem, and a few numerical results and remarks. The motivation of this work is that to prepare and to develop a thermal model for finding the temperature distribution of different parts of an electric motor during its various operating conditions. The motor temperature is closely linked to the life and the performance of the electrical motor. There are three types of thermal risks. The first one, the stator winding temperature can affect the winding insulations. The second, the winding resistance is proportional to the temperature. That means that the higher resistance will be equivalent to have higher thermal losses. And another problem is in the rotor. When the rotor is very, very high, that can affect the efficiency of the permanent magnet, because the magnet is very, very sensitive to the demagnetization at elevated temperature. In order to avoid the overheating problem, heat generated in the PM motors should be transferred toward outside air, and it's essential to have a detailed knowledge of the heat exchange in the PM motor. The prediction of the temperature distribution in an operating electric motor is required at the machine design stage. Now, our motor, it's here. This is the prototype motor, and here it's the CAD model. And it's our motor, it's an exterior radial fluxus. That means that the magnets are located outside the winding, and the stator and the winding are difficult to cool. And the geometry of our motor is only enclosed, that you can see here. And the power of this motor is about 11 kilowatts. Here, a few photos. This is the stator and the winding part of our motor, and here it's the rotor. And here we have the magnet. And this part go inside of this rotor. And we do some measurement, and you can see the localization of our thermocouple to take the temperature of this part. Now here is an exposed view of our motor. It's look like that. It's here the winding and the stator, and here is the rotor. The geometry of the rotor is a hollow cylinder, and it's a fixed stator, which is here. It's located within the rotating rotor. The stator slot is filled with one material only. It's here, it's the winding. This is the copper. And the winding region is modeled as solid region, because here we have three material. We have the copper, we have the insulation material, and we have the air between the electrical part. And the head of our winding, it's modeled as torus. The calculation of this model, the thermal calculation in this model, we do that in Fluent Abacus under this, using this mesh. It was about 10 million. And here in red, this is the fluid part, or the air gap. And here we have a section of our air gap. It's very, here we have a very narrow places between the magnet and the stator winding, and here. I think the first will be the CFD computations. We use Reynolds average Navier-Stokes equation using turbulence method 2, and we impose a temperature in the boundary of the winding and stator, and we use approximately 5 million cells. Here we have the contour of the velocity, the contour of the temperature. Here, streamline obtained at this. And here we do that with very small rotations. Here, different view of the streamline obtained by Fluent. And in the solid part, we do the calculation with Abacus, and here we have the Atgeirr motor, and here only the winding part. And you can see the difference between the two heads obtained by Abacus. Now, when we talk about thermal model, we need, in the motor, we need to talk about motor losses. Power losses in the PM motor are an important consideration, as they are dissipated in form of heat, hence they act as energy source in our computational thermal analysis. And we have some losses. The first one is the winding copper losses. This is the classical Joule losses, Joule effect. Is the product of the resistance of the square of the current. And we have other losses, core losses, which become for the eddy current losses and the hysteresis effect. I give here the formula to calculate this type of losses. We need the flux density and the frequency. In this calculation, in the first time, we don't take an account for these losses. And we have other type mechanical from the fraction losses, the contact between a part, solid part of the model. Thermal analysis Customary, we solve that using finite and in the motor, and the finite element, the coupled finite element and the composition fluid dynamic analysis, which mean that we use finite element in the solid part and the CFD in the fluid part. And we need to do some communication between the two parts, and you see the hot fluxes come from the fluid, and the temperature as boundary condition come from the structure. And it's well known that the CFD is very, very complicated. We need use turbulence model to capture all effect in the interior of the motor. Now, conjugate head transfer. I give here the equation because for FAIR++ we need to start from the model. Here we have in the solid part, the temperature have to satisfy this equation, and we have the second member of this equation is come from the electrical losses. And the second part in the fluid, here we plan to model with using incompressible Navier-Stokes equation with Boussinesq's approximation. And here they are the system that we have to solve. The continuity equation, the momentum augmented by the Boussinesq approximation, and the last equation we have the energy in the fluid part. Source of model. Here, how the method to calculate the losses in the motor. As I say in the 5th slide, we will calculate only the losses coming from the Joule effect. And for that, we use electrostatic model, which means that the electrical potential field in the conductor is governed by Maxwell equations. And this equation can be written in the steady state cases in this form. After that, we use the constitutive equations with a relation between the electrical field and the current density. And after that, we need the balance equation express the conversion of the charge. This is the Gauss law. It's written in this form. And after that, it's very easy to, using the previous equation, we obtain the Poisson equations. We need to solve this problem. We need a few boundary conditions. Here, prescribed electrical potential, and we can give, as Newman, the current. And after that, when we have the potential, we can calculate the Joule losses by these equations. Now, the proposed or the planned model to solve the thermal model in our cases look like that. In part, this equation in the solid part, these equations in the fluid part, and in the winding, we have to solve that to calculate the losses. And this is a very, very nonlinear problem, nonlinear coupled problem. To solve that, I don't go in the detail how to write the variational equation of each equation. I use a few notations here. We introduce these notations, which the first component is the velocity and the pressure. It's coming from the fluid part. The term temperature is coming from solid and fluid part, and the potential. The first problem, it's in the solid one. This is the potential. No, the first one is the fluid part. The second one is coming from the temperature, and the last one is coming from the potential. To solve this problem, nonlinear problem, customary we use Newton methods, which look like that. We have to write our equation, the first order of the Taylor series, and here we have the first derivative with, in this case, is the Jacobian of the matrices, and here the iteration functions. And here we have a lot of zero because the dependence in the second we have only temperature and we have velocity too. We will have a lot of zero in this matrix. Now, the algorithm to implement, it's the customer algorithm. We start by to compute the Jacobian and the residual, and we have to solve that. And we have to do that, that's these two quantity, not the product. Yeah, these two quantities have to be small. And this is a planned algorithm to solve our thermal problem. Actually, I don't have implement that because I have some problems, but each problem, for example, the thermal, it's not difficult to implement that in the solid. The potential using FEL++ program, the potential too is not difficult to implement. But using this couplet problem, I have a small problem. I don't have a result about that. Now, the first numerical result. The first example, it's only we solve the conduction problem in the winding stator only because when I use the old model, which it's about more than 10 million cells, I have a problem with MPI. Actually, it don't work. But using my program, we can. It was able to using FEL++, able to calculate the temperature in the stator and the winding. The second, here I use a smaller model. Here, the dimension of our model is the same, but we use here coarser meshes because to solve the condition problem, we don't need very, very fine element. Here it's the 8 of the domain, and we can see here we have rotor stator here, and here we have the gap, air gap, we have the magnet, and it's here. It was about 120,000 cells using FEL. The same, but here we use I use the Carter of this model, the motor model, and we have the same compartment of our solution. And we have used here double number of the cell. Now, for the coupled conduction and potential problems, it was impossible to calculate the potential in the previous geometry, where we have only the winding and the stator, because I have a high gradient of the potential in when I calculate the potential in this geometry. And using this potential, we have very, very high temperature. Because this geometry, it's not adequate to use for electrical method, for electrical problems. And I do another geometry when I drop the head of our winding. You can see here without head, and I put the potential. Here we have the winding only. You can see here we have the stator, and here we have more. We have the air gap, we have the magnet, and we have here the support of the magnet. And you can here that's work correctly the potential calculations, and here it's here the potential in the other side, and here it's the temperature. The same with other value of the potential. And the last one example is a very small example, but here we can see we have a domain. Here we have a conductor part, here isolant part, and here we have at the middle the temperature is very, very high. And it was the last example. Thank you very much for your attention, and it's time for questions.
Are there any questions? No. Sorry.
Thank you. Okay. Can you see any difference between Abacus and Fil++ at this stage of the research?
Yeah, but I think this is not a problem for Fil++. It's the problem of our computer. I see that the time computation, it's not very, in Abacus it was very fast. It's fast, actually, but it's not the problem of Fil++, I think. It's our system that we have a problem. Because for the condition problem, when I want to use a bigger model, the computation start, the first iteration, but at a certain moment they block because I have an error, MPI don't work, kill something. And we have to do that in Plexi, and after that I can do comparison.
Okay, thank you.
My question is more computer-oriented. So, would you be willing to run your simulations in the cloud, for example, or do you have any constraints? If you imagine you could access to Fil++ to the software using cloud computing instead of using your cluster?
Yeah. But actually, I do only in our machines.
Yeah.
But we have another machines, a bigger one, Plexi, with more memory and more. more thorough. And after that, if they don't work, I will use your machines.
Maybe, I mean, the objective is not to use our system, but to be able to access the resources in a transparent way. I mean, even the plexiglass.
This is the purpose of work. But actually, we want to use our material, and after that, well.
Okay, good. Thank you.
Okay, so we can move to the next presentation. So Christophe Trophime on the modeling of high-field magnets.
Okay. Good morning, everyone. So I will present you the Hifimagnet, which is built on top of Field++. So Hifimagnet is a platform for modeling and simulation of high-field magnets. So I will briefly present you the context, because one of my colleagues will give a talk on that topic tomorrow. So high-field magnets are essential ingredients for large research area. We can quote, for instance, the LHC in Geneva, where they are really big magnets. And these magnets serves to control the beamline, but also serves for the experiments. And for instance, in these big ones, so the magnets are here, by the way, they managed to discover the Higgs boson. Here you have another example, which is an NMR magnet, which is designed to study the functions of brain, and is actually built in Paris at the Neurospin facilities. And here you have some more common magnets designed for NMR, and they are especially used for chemistry or biochemistry. So at the LNCMI, so LNCMI stands for Laboratoire National des Champs Magnétiques Intenses, is a user facility run by the CNRS, which is in Grenoble and in Toulouse. So here in the lab, we are designing high-field magnets, mainly for solid-state physics research. The broad of research performed in our magnets is extending right now to MHD, for instance, magnetohydrodynamics, for instance, studying the origin of the Earth magnetic field. And we are also developing some magnets for ion sources. So this facility may be accessed through calls, and if you like, you can perform experiments in our lab. So here are the technology we are using to get that high-field magnets. So these are not superconducting magnets, these are resistive magnets, because we provide field which is beyond 25 Tesla, and 25 Tesla is right now the limit for existing superconductor. So some figure, these magnets are powered by a 24 megawatt installation. That means we have currents which go up to 30 kiloamps. So these magnets have to be cooled down by water flow. So the water is about 30 meters per second within the cooling channels. And with that kind of magnets, we can reach 36 Tesla in a 44 millimeter bore. So basically, for all these projects of big magnets, users are looking for the highest possible magnetic field, or for some what I call magnetic field quality, either in terms of homogeneity, if you think of NMR magnets, or some very specific profile, for instance, for ion sources, or for the magnets which control the beamline in the LHC. So these big magnets represent some design challenges besides the technical ones. And by technical ones, I mean the problem in terms of materials, for instance. So we have to cope with nonlinear multiphysics. We have also to account for uncertainties in terms of physical properties of the materials, in terms of geometry and mechanical clearances, and also in terms of operational conditions. This is really needed to achieve what the users want and to have some robust and efficient design tools. So this is the typical workflow for developing magnets. So we start with some optimization on some simple geometry, making a lot of assumptions to be able to carry out this optimization. We end up with some basic design. From this design, we built a mechanical structure which represents our magnets. Then we turn again to numerical modeling to see if these magnets will meet the requirements in terms of fields, in terms of constraints, thermal constraints, mechanical constraints, and so on. This magnet is validated through several experimental experiments, and then the magnet is set into operation. Of course, if something goes wrong, we have to loop through this again. So the idea of this Hifimagnet project is to provide a range of multiphysics model, to start from very simple models, axisymmetrical models, and to go to complete 3D models, including more and more physics. What we want is we want to have some efficient models to be able to carry out these complete 3D models. So we need HPC in that context, and even more, we need some reduced order models to be able to perform uncertainty quantification, sensitivity analysis, to go towards robust design. Okay, so the project is mainly devoted to what I call solenoidal configuration, which is basically represented in this sample magnets here. So the idea is to provide some automated CAD and meshing facility for this kind of magnets, to provide numerical models ranging from axis models to 3D, to be able to perform some sensitivity analysis and uncertainty quantification. So to do that, we relies on several tools. So magnet tools, which are in-house LNCMI software, which covers the first step, that is the optimization, which is based on analytical calculation. Then we use Salome and MeshGems to create the CAD and to mesh. As for the physics, we are building our models on top of Field++ boxes, and we are using ParaView for the post-processing. So I will go into more details. So here is a plugin we have developed within Salome to perform the automatic geometry generation and to carry out the meshing all automatically. So here you have a sample of a 14 helices insert, which provides something like 36 Tesla. So as you can see here, this is a small example of a script that you can run to create automatically this geometry and mesh it. Okay. As for the multiphysics modeling, it has many similarities to what has been presented before. So we have to solve, of course, the Maxwell equation, which will give us the magnetic field. As there is high current flowing into the magnets, there are a lot of Joule losses, so we have to deal with heat equation. The magnet has been need to be cooled because of that Joule losses. So we have also to consider the coolant flow within the magnets. So far, this model is only done by some very, shall I say, rough modeling, which is to consider convection heat exchanges using standard correlation to have access to the heat exchange coefficients. And finally, due to the Lorentz forces and the dilatation, we have to consider the elasticity to get the maximum efforts within the structure. And of course, all of these are looped because first of the physical property, which depends on the temperature, and they are looped also because of the deformation, which may act on the cooling, which may degrade actually the cooling, and then change the dilatation and the property and so on in the loop. Okay. So here are some examples of the calculation. So here we have an example of an insert which has been modeled with something like 30 million of unknowns. So to perform the whole loop, we need a rather huge memory, and it runs in something like 1 hour. Okay, here are an example of the 3D magnetic field created by such kind of structure. And what is interesting to notice here is that for the first time it was observed that we have some clear 3D magnetic effects here. We can see here. This is a radial magnetic field at the output of the magnet along a circumference. And it was believed in the past by experts in that community that that kind of magnets have almost an axisymmetrical behavior, which is obviously not the case. And we have performed experiments to see that effectively we have this same kind of behavior. Okay, so finally with the model we can also compare on the see if I have a pointer. No. Okay. Oh, here I am. So we consider uncertainties on the physical property of the material here, and also uncertainties on the operating conditions, and especially on the water cooling model. So here is the heat exchange coefficient, and here is the temperature of the water. So using the reduced basis methods, we can perform a lot of calculation, because we have mainly again about a factor 150 for a computation of such kind of model. Okay. So we have some interesting information about the mean temperature and the deviation from the standard. And we have in that case what are the main parameters. Well, obviously it's the current which is the main parameter. But what is interesting is that the second more influenced parameters are the one from the, well, actually the temperature from the water, and then only the heat exchange. And the parameters, well, connected to the material properties have almost no influence. So this kind of information is really interesting from a designer point of view, because it says that we have to put more emphasis on trying to find a way to act on the water temperature instead of trying to improve our material properties. And finally, we have also access to nice information which are quantiles. So quantiles is a way to tell that we are sure that for this kind of magnet, the temperature will not exceed 130 degrees at 99%. So this kind of information may be really interesting for the control command system, because we have very tight threshold for the security. Okay. So from a practical point of view, the practical workflow for the user is the following. So we start giving some, starting from some files, we perform the optimization. This optimization is used to generate some files to carry out the CAD and the meshing generation almost automatically. Then the user has to fill some configuration files to define what he wants to perform in terms of calculation. Okay, only the thermoelectrical model or the all loops, for instance. And then we will use ParaView to have access to the results. So far we have not customized ParaView to get some images through some scripts or things like that. Okay. So in terms of installation, all the sources are stored on GitHub right now. The software is built on top of custom packages, also for Fil++. We use these packages to create a Docker image, and this Docker image may be readily used by users. In our lab, most of the designers are using Windows and not Linux system. So here you have a simple example showing you that the CAD is running directly through Docker within Windows 10. So what we want to go one step further, which is to be able to have a continuous deployment onto our computer using some kind of tool like Buildkite. So to sum up, we have somehow simplified all the process of installation. We have simplified the use of the whole chain through the use of JSON file for the configuration. We have improved a lot the code by creating some test suites. And there is actually we are actually developing the documentation, which may be accessed by the users from that website. So it means that in terms of deployment, we are almost ready at this point to have Hifimagnet to be used no longer by me. We develop it partly, but to be used by people from the what we call in French bureau d'études. I don't know in the translation in English, sorry. So the designer, the guy who actually makes CAD and so on. So they are ready, the code is ready to be used by them. So, okay, that's it. Thank you for your attention, and if you have, can show you the website, what it looks like. Okay, let's start with this. So, it looks something like that. So you will find there all the information you need to be able to create a geometry. It's not fully ready, but so you have the commands here to start Docker, the Docker image, and here an example of the scripts to create that kind of geometry, which is rather complex. Okay, and here you found the same example. Okay, I move to the little demonstration. Okay, so here I have let's see. So here in this small demo, we will see how to start the Docker image. So here is a list of the available Docker images. So we're gonna start the Salome Docker images. Well, one of the technical difficulty here is that the Salome is using OpenGL, so you have to do some more stuff than usual. Okay. Okay, so here we start Salome. Maybe I can skip. Okay. So it took some time because I recorded the video at home and I have a very poor connection. Okay. So we create a new geometry here. So in that sample, I will take a very basic sample, which is a torus, right? So you simply create the torus. We extract here the shell of the torus to apply a boundary condition on it later on. Okay, and then we move to the mesher. So we create a mesh. We choose the meshing algorithm. So in that case, it's mesh gems. We slightly change the parameters. Okay. It's stuck. No. Okay, here I miss. Up. Okay, so here I missed some. I made a mistake because I chosen not the right CAD at the beginning. So, okay. So here I just compute the mesh from the surface, in fact. And here you have an image of the mesh. So starting from that, you can record all the session, dump it to a Python script that you can replay at any time. I think we can stop with that. Je vais peut-être laisser. And Guillaume will show you the use of.
So I will show you a demonstration of the Docker applications of Hifimagnet. So maybe you can run the movie. So actually the current image, Docker image, is not built automatically, as said just before Christophe. But it should happen quite soon. We will make it with continuous integration to have, for example, the Docker images and Singularity images automatically generated and then provided online for everybody. Okay. So here I just make a demonstration of the Docker images running on the cluster. So it's our own cluster because we have Docker there. So first we have to run a Docker container. So you have a lot of options because we want to have the graphic parts and we want to have access to some licensed servers for using mesh gems, which is a tool to generate some mesh. Okay, so we are, as you can see here, we are in the containers because you have the prompter which shows that you are inside. So we are running the containers interactively. Okay, so you are not obliged. If you want, for example, you can use directly a job script using Slurms to run your applications. Actually, it's the good way to do it would be to use batch jobs. Okay. So then, as you see, I mounted some directories to have all the examples inside the containers, and I will run the Fil++ applications inside the containers in parallel. So here, for example, our application is called the FilPP HFM thermoelectrics model. So it's a thermoelectrics models, and you have the configuration script, which is passed by option here. Inside these configuration scripts, you have some JSON files that describe the two models. So for the thermo part and the electrical part. So okay, let's run it. So you have a lot of warnings, but it's not a problem actually. It's because of InfiniBands. But we don't use InfiniBands here because we are on only one node. So as you can see, you have a lot of informations that are printed out on the terminal. So for example, where the file is stored. Okay, then you have the generation of the mesh. You have some information that are printed here that you can get afterwards. So and then, okay, the simulation is running. So you have some information on the models, for example, the potential, the temperature, that are very interesting. For example, if you want to check that your model is running fine. So now it takes a little time. I will just jump. After. Okay. Up. So I cheated a little bit in the video. So I have already the results of the simulation. So what I will try to show you is to use a remote connection with a ParaView server to connect. So from here to Strasbourg, because actually it's a cluster of Strasbourg that I am using. So we are running on the right side a ParaView server. Okay, then I will try to connect. So I get the first. Okay, it's just here. So here in ParaView, you can connect, for example, remotely on a ParaView server. So as you can see, for example, the client is connected. Once you are connected on the server, you can access to all files that are available on your servers. So it's remote. Actually, it's the server who is rendering the simulation, and you are just visualizing on your machine. Okay. So I open the exported files.
It takes some time because it's remote. You have the connection was not really good. Up. So then you can visualize the results that you get from the computation. Okay, so it's an example, for example, of one helix of Hifimagnet example. And if we look just a little bit after, we can see the mesh. Okay, so as you can see, it's quite a fine mesh on the helix. So it's the visualization is performed remotely, and as you can see, the simulation is just terminated here. It takes like 300 seconds, I guess. Yeah. Okay, 296 seconds exactly. Well, that's it. So, if you have any questions or comments, you're welcome. No questions. So everything is understood.
Chairman, you are the chairman.
But I don't have any questions. I mean, I know I know how it works. So no questions? Okay.
You show the Docker container and you run it on Windows, and you mentioned that a number of your envisioned users are using Windows. Do you see that as a main reason for using Docker?
No, the main reason is to simplify the burden of installing all the libraries and so on. It's well, the main reason. Well, the other is it's really convenient for me because all the platform is developed in Linux and the user are on Windows, so it's a way to solve that problem again. But it was not thought on that basis on the first time. The idea was really to simplify the ports, and especially in the frame of this project, the idea is to really try to use in the future this Docker, both on the Windows laptop from the designer, but also to use it for connecting to servers just like Atlas in Strasbourg to perform calculation. I really want the people from my lab, and hopefully for overlaps, to use that kind of tools to design their magnets.
Actually, it's a good question. Regarding Windows, with Windows 10 you have the bash now. Unfortunately, you don't have Windows 10 on a lot of workstation. I mean, usually the IT departments it's complicated, also in companies. So Docker really solves the problem here for us to deploy solutions. I mean, we've seen it. I mean, this changed things for us in a huge way. But there is also an interesting point about using this kind of technology, Docker or another one, this container technology, is reproducibility. That is, when you add some results, you can go back to the version of the container you used in order to get the result. And for some companies or for some people, it's actually an important feature, reproducibility. Make sure that it's not like you push a button once, you got this result, and then you are just lucky about it. So this is an important topic for some stakeholders.
To add just a comment about Bash on Windows. When building the Docker images, I rely on homemade Debian packages from Phil++ and their requirements. So my idea was also to use later on that packages to be able to install directly on that sub-Linux system on Windows, to install directly all the software within it. Right now, my experiments is the system is not really really proof, because there are a lot of problems with antivirus and so on. So I expect we have to wait a few years before it really becomes a reality, but it's clearly also an alternative for Docker. But right now, Docker seems to be, or at least the container technology seems to be more efficient from a practical point of view.
I use Docker and Windows, but I have a problem when I write my own applications, and it's impossible to compile these applications under Docker installed in Windows. It's possible to use all applications, executable program, but writing my application and compiling, it's not possible now. And
I tried several approaches. I mean, I tried to have a container for all parts. That is one container only for Salome, one container for Fil++ and Hifimagnet, and one container which contains the whole things. Okay, and I think you can't really use either Docker images. The point is that the more software you put into an images, the bigger the images gets, and you may have trouble with big images. I don't know. I mean, it's a rather new experiment, to be honest, but it seems to be working. And as for the building the Docker, they are built on a Debian machine, and it works almost without problem.
I think it's a good idea to develop the Docker under Windows, because a lot of students use that. For educational purpose, we can use that.
Any other questions?
I have a question related to, in general, the models, because I was attending this event last week at HPC, and there was some sessions about mathematics, and one of the topics which was mentioned was the complexity of multi-physics simulation, multi-scale, and somehow it was expected that these kind of simulations would make a good use of near future exascale systems. So I would like to know to what extent you expect your models to be more and more complex in that multi-physics aspect, and how do you think that you could scale in the amount of resources you may need to consume for doing the computations?
Well, it's a difficult question, but okay. So as for our model, so we have developed a strategy which is what we can call weak coupling to tackle multi-physics. So we have a Fil++ toolbox for each of the physics. So right now, besides the cooling part, what we have done covers almost all our needs right now. But in the world of Hifimagnet, one important thing is to move towards superconductor magnets. And superconductor magnets are much tougher from a physical point of view. First, because the nonlinearity is stronger than what I get here. So we may have to have some more strong coupling. That is, instead of having one toolbox for each physics, we may need to put all the physics within one big system, so it will be more difficult. So I expect that in the future we will have a big requirement in terms of calculation if we want to move to superconductor.
Okay. Okay, thank you.
So under normal operations, is this elasticity aspect in the couple problem, are there large deformations, or is it?
So right now what we have implemented is only the linear elasticity. So we expect also to try working on first anisotropic models, because we have some anisotropy, well, problem with anisotropy properties, and move to plasticity. But in that kind of models, deformation are rather small.
So it's only if in like risk analysis and when
yeah,
in failure.
For that kind of things.
Post-mortem analysis.
Yeah,
Post-mortem
right.
diagnostic.
Mm.
Typically the elasticity module is...
But if everything's go very well with that kind of project, I mean, we can expect colleagues from Toulouse to use that kind of things. In Toulouse, well, in Grenoble, there's something I didn't mention in my talk, but in Grenoble, we are focusing on what we call steady fields. That is, we are operating the magnets at 36 Tesla for 6 hours. That's a typical run for the user. In Toulouse, they are reaching almost 100 Tesla, but within some hundreds of milliseconds. And they have projects to go even higher, but with very simple coils, but which are completely destroyed after the shock. And they may be interesting by having large deformation to improve their design and so on. But right now it's, well, beyond the scope of what I'm trying to do. But it will be very interesting to see my colleagues from Toulouse getting involved in the project and designing big magnets.
So when you identify the most important parameters, you did a sensitivity or parametric study?
Well, actually we use a reduced order model to
that's where from you got these numbers.
Yeah, so we use a reduced order model to make something like 600 realizations, and then we use open turns to carry out the sensitivity analysis on top of this data.
Yes, I was curious about where this...
So regarding the UQ system, so if you use Monte Carlo, then you would need a lot of evaluations. So you replace your model with a reduced order model. That's what we do, and we developed a reduced basis for nonlinear problems, which with relatively low budget for the reduced basis construction. And then we don't do Monte Carlo because here, as you saw, it's only the first order Sobol indices that we actually compute. Is a Sobol indices we compute. So we use polynomial chaos to build yet another reduced model. And from the polynomial chaos expansion, you can retrieve at a much lower cost the first order Sobol indices. Okay. So that's how we do it. But we could do Monte Carlo because it's like orders of magnitudes cheaper.
Thank you.
Other questions?
Last one, but I see that you do your computation with about 27 millions. Is this? I hope that I can use one model with this number of elements.
So I didn't catch the question.
The question, it's the version that you use to calculate that is the same that than in the net or the Docker version.
Yes, it was in the Docker version, but
Yeah.
it's rather long because we are using some PCAR iteration. So going for Newton Raphson, we should end up with 6 iteration instead of 15 or something like that. So we can expect some gain.
Yeah, the problem, it's our problem now with our computer, not with the
The model is here. You have to change a few things. And most important is that the same model can run on my laptop and in Strasbourg on a bigger computer.
Yeah, not only. So actually, for the model that I use, the maximum was 2 millions. More than 2 millions, there are crash, MPI crash.
No, yeah, it's working.
The technical problem.
Okay, so let's close. I think unless there's, you can always ask Christophe or Guillaume regarding the how the tool chain was put together. Thank you, and we finish now for the morning.